a telescope $10 billion in the making just stared at the early universe. What it found could rewrite the laws of physics. We're talking about a ring of galaxies 1.3 billion light-years wide, a wall of matter 10 billion light-years long, structures so enormous they flat out shouldn't exist. If you enjoy mind-bending discoveries like this, hit subscribe so you never miss one. We'll trace how Webb mapped 800,000 galaxies, found stars born way too early, and detected a structure that may force us to delete an assumption that holds all of cosmology together. Brace yourselves. We begin. For most of human history, we thought Earth was the center of everything. Then we figured out we orbit the sun. Then we discovered our sun is just one of hundreds of billions of stars in the Milky Way. Then we found the Milky Way is just one of hundreds of billions of galaxies. Every time we zoomed out, we got smaller, but we held on to one last comfort. At the biggest scales, the universe is smooth, even. The same in every direction. No special place, no giant lumps, no impossible shapes. Matter spread out like sugar dissolved in water. That assumption has a name. Cosmologists call it the cosmological principle, and for decades, it worked perfectly. Every telescope we pointed at the sky confirmed it. Every computer simulation we ran agreed. The universe, viewed from far enough away, looks like a calm, even sea. That picture is now cracking. The cosmological principle sits underneath almost every equation in modern cosmology. It is the foundation on which scientists calculated the age of the universe, the speed of its expansion, the amount of dark matter and dark energy holding everything together. Pull it out, and the whole structure wobbles. This is not a small technical detail hidden in a journal somewhere. This is the second most fundamental assumption in all of physics, after Einstein's theory of general relativity itself. One physicist described what happens if it breaks like this. All hell breaks loose. So, what scientists assumed was that if you zoomed out far enough, maybe 500 million light-years, maybe a billion, the universe would average out. Big clumps here, big empty spaces there, but overall, smooth, like looking at a city from a satellite. Up close, you see buildings and streets and parks. From space, it blurs into a grey uniform smudge. That is how the universe was supposed to look at large scales. Every major cosmological model assumes this is true without even questioning it. It gets plugged into calculations like a known fact. Here is what makes this assumption so fragile. It has never actually been proven. Scientists adopted it because it matched observations, and because without it, the math becomes nearly impossible. It is a working hypothesis that became treated as settled reality. And now, one after another, telescopes are finding things that should not exist if it is correct. A team studying the sky in 2021 found a curved wall of galaxies, almost 3 billion light-years long. Scientists calculate that structures above 1.2 billion light-years should be physically impossible given how the universe formed and how much time has passed. That wall was almost 3 times past the limit. 2 years later, the same researcher found a ring of galaxies in the same patch of sky, over 1 billion light-years in diameter, perfectly shaped, unexplained. And those two discoveries are small compared to what was detected even earlier. A structure 10 billion light-years long, so enormous it cannot be photographed, only inferred through the dying screams of massive stars. Each of these structures pokes a hole in the assumption. Together, they are starting to look less like measurement errors and more like a pattern that our best theories have no answer for. Before we get to what these structures actually are, we need to understand the machine that brought the crisis to a head. A gold-plated, tennis court-sized, 21-foot miracle of engineering that has been staring at the edge of time since Christmas Day of 2021. On Christmas morning in 2021, a rocket lifted off from the jungle coast of South America. Inside its nose sat the most expensive scientific instrument ever built, $10 billion, 30 years in the making. Originally planned to launch in 2007, delayed again and again, its budget ballooning from 500 million to 10 billion. Half the astronomy community had spent their entire careers waiting for it. The other half had given up hope it would ever fly. The James Webb Space Telescope folded itself origami style to fit inside the rocket. Its main mirror, 21 feet across, made of 18 gold-plated hexagonal segments, had to collapse like a flower closing its petals just to squeeze into the payload bay. A sun shield, the size of a tennis court, folded into layers thin as human hair. Engineers had designed over 300 individual mechanisms that all had to work perfectly in the right sequence after launch. Every single one did. 29 days later, Webb finished unfolding 1 million miles from Earth. That distance matters. The Hubble Space Telescope orbits 370 miles above the ground, close enough that astronauts could fly up and fix it by hand, which they did 5 times. Webb sits at a gravitational sweet spot called the second Lagrange point, where the gravity of the Earth and Sun balance out perfectly. Nobody is going up there to fix anything. It had to work on the first try. The mirror is coated in a microscopically thin layer of gold. Gold reflects infrared light better than almost any other material, and infrared light is what Webb hunts. Here is why that matters. The universe has been expanding since the Big Bang. As light travels across billions of light years of expanding space, its wavelength gets stretched, like sound from a car that drives away from you. Visible light, the kind human eyes detect, gets pulled into the infrared range, which is heat radiation, invisible to us. Webb is specifically designed to collect that stretched, ancient light. Hubble could not see it. Webb lives in it. The sun shield exists because Webb itself must stay incredibly cold, around -400 degrees Fahrenheit. The slightest warmth from the sun or Earth would overwhelm the faint heat signals coming from galaxies 13 billion light-years away. The 5-layer shield blocks that warmth so completely that engineers compared it to sun protection of 1,000,000 times the strength of the strongest sunscreen ever made. When scientists aimed Webb at a patch of sky that looked completely empty, about the size of a grain of sand held at arm's length, they found thousands of galaxies. Some of those galaxies existed when the universe was less than 500 million years old. For context, the universe is 13.8 billion years old now. Webb was staring back at its infancy. Every image Webb sends back is a time machine photo. The light it collects left its source millions or billions of years ago and has been racing across space ever since. When Webb captures it, that light is ancient history arriving in real time. The farther Webb looks, the deeper into the past it sees. And the past, it turned out, looked nothing like what we expected. The first images landed in the summer of 2022. Within weeks, astronomers were already arguing. Something was wrong, or something was right, and our understanding of the universe was wrong. Every time you look at the night sky, you are looking into the past. The moon you see is the moon from about 1¼ seconds ago. The sun you see left its surface 8 minutes and 20 seconds before it hits your eyes. The nearest star beyond our sun, Proxima Centauri, appears to us as it was 4.2 years ago. The Andromeda Galaxy, the closest large galaxy to ours, shows us what it looked like 2.5 million years ago. Ancient history, arriving in real time. This is because light travels fast, but the universe is vast. Light moves at about 186,000 miles per second, the absolute speed limit of the universe. Nothing moves faster, but space is so enormous that even at that speed, light takes an almost incomprehensible amount of time to cross it. A light year is simply the distance light covers in 1 year, about 5.9 trillion miles. And galaxies are billions of light years away. When astronomers point a telescope at something 10 billion light years away, they are not seeing that object as it exists today. They are seeing what it looked like 10 billion years ago, when that ancient light first set off on its journey toward us. The telescope is not just a magnifying tool, it is literally a time machine. The farther it sees, the further back into history it reaches. This is why Webb was built. Hubble could reach back about 13 billion years in some cases, but with limited detail and only in certain wavelengths of light. Webb pushes that capability further and in far more detail, capturing the universe as it looked when it was only a few 100 million years old. The Big Bang happened 13.8 billion years ago. Webb can show us the universe when it was barely out of its infancy. There is a practical effect of all this distance that shapes everything Webb sees. As the universe expands, the space between galaxies stretches. Light traveling through that expanding space gets stretched along with it. Wavelengths that started as visible light, blues and yellows and reds, get pulled into longer wavelengths over billions of years of travel, shifting into the infrared. By the time the light from the earliest galaxies reaches us, it has been stretched so far that no human eye and no ordinary camera can detect it at all. Webb's infrared instruments were built specifically to catch this stretched ancient light that Hubble was mostly blind to. Think of it this way. Imagine throwing a ball across a room where the walls are slowly moving apart. By the time the ball reaches the other side, the room is bigger than when it started. The ball took longer to arrive than it would have in a fixed room. Light does something similar, crossing, expanding space. The journey changes the light itself. What this means is that every Webb image of a distant galaxy is a snapshot of a younger universe. Scientists can line these snapshots up in order of distance and essentially watch the universe age, from its chaotic early years through billions of years of change to today. That timeline is exactly what astronomers began constructing with Webb's data, and the timeline they found had a problem. Some of the earliest galaxies on it were far too big, far too bright, far too organized. They looked the way galaxies look after billions of years of growth, except they were sitting in snapshots taken when the universe was barely a few 100 million years old. The timeline made no sense. That problem starts with what was supposed to be there first, before any galaxy ever formed, something invisible, cold, and absolutely essential to everything. Before the first star ever burned, before any galaxy took shape, before any planet formed, the universe had a skeleton. You cannot see it. No telescope can photograph it directly, but it is the reason anything in the universe exists at all. Scientists call it dark matter, and it outweighs everything you can see by a factor of 5 to 1. In the first moments after the Big Bang, the universe was a sea of hot, dense particles flying in all directions. It was close to perfectly smooth, but close to perfectly smooth is not the same as perfectly smooth. Scattered across this early universe were tiny variations, patches where the density of matter was just barely higher than everywhere else. These patches were small, random fluctuations that would look totally insignificant to any observer. They were anything but. Dark matter does not emit light. It does not absorb light. It does not interact with ordinary matter except through gravity. So while ordinary matter was bouncing around in that hot plasma, radiating and colliding and being pushed in every direction, dark matter was quietly doing something else. It was responding only to gravity. And gravity, given time, always wins. Those tiny patches of slightly higher dark matter density began pulling more dark matter toward them. Slowly at first, then faster. Over millions of years, the patches grew into clumps. Clumps grew into halos, enormous invisible spheres of dark matter, anchored in space by their own gravity. These halos became the most important structures in the early universe, because wherever a dark matter halo formed, ordinary matter eventually fell in after it. Hydrogen and helium, the raw materials of stars, swirled into these invisible gravitational traps. The gas compressed, the pressure rose. Eventually, the compression became so intense that nuclear fusion ignited, and the first stars in the universe blinked on. Those first stars formed inside dark matter halos. Every star you see in the night sky, Every galaxy visible through any telescope sits inside a dark matter halo. The halo came first. The halo is why everything else exists. Imagine the dark matter skeleton as the steel frame of a skyscraper before any walls, floors, or windows are added. The frame is invisible to someone standing outside, but every visible part of the building is hanging from it. The dark matter web is the frame of the entire universe. Galaxies are the decoration, but dark matter halos grow at a specific pace. They merge slowly, hierarchically, small ones combining into larger ones over billions of years. Cosmologists have modeled this process in extraordinary detail. Their simulations predict very precisely how many large dark matter halos should exist at any given point in the universe's history, and therefore how many large, massive galaxies should exist at each point in time. This is exactly where James Webb began causing problems, because when it looked back at the early universe, it found far more large galaxies than the dark matter halo model predicts should have been there. The halos were supposed to be small in that era. The galaxies hanging inside them should have been small too. They were not. Some of them were enormous, comparable in size and mass to the Milky Way, fully assembled, blazing with stars, existing in a universe barely old enough to have started building the structures supposed to host them. The invisible skeleton appeared to have been skipped somehow. But before that mystery can make full sense, there is one more piece of early universe physics that explains why structures in space have a size limit at all, a size limit that the structures Webb discovered appear to have completely ignored. About 400,000 years after the Big Bang, the universe did something remarkable. It went quiet. In the beginning, the young universe was a single roiling ocean of matter and energy, unimaginably hot and dense. Sound waves moved through it constantly, compressions and expansions rippling outward in every direction. These were not the sound waves you hear on Earth, vibrations moving through air. These were oscillations moving through the matter and energy of the entire universe, waves that carried enough energy to sculpt everything. As the universe expanded and cooled, a moment arrived when the temperature dropped enough for electrons to finally bond with protons and form neutral hydrogen atoms. Before this moment, electrons were too energetic to stay attached to anything, bouncing freely through the plasma. The instant they settled down, the universe became transparent. Light could finally travel in straight lines instead of scattering off free electrons. That light has been traveling ever since. We detect it today as the cosmic microwave background, a faint glow of ancient light coming from every direction in the sky, the oldest light in the universe. But the really important thing about that moment of quiet is what it did to the sound waves. When the universe turned transparent, the sound waves stopped. They froze in place, locked into the distribution of matter at that exact instant. The compressions, the crests of those ancient waves, marked spots where matter was slightly more concentrated. Those spots became the preferred locations where galaxies would later form. The troughs between the waves became the preferred locations for vast empty voids. Scientists call the imprint of these frozen sound waves baryon acoustic oscillations. Baryons are particles like protons and neutrons, the ordinary matter that makes up everything you can touch. Acoustic means sound, oscillations means waves. So baryon acoustic oscillations are essentially the fossilized ripples of the universe's first sound, stamped into the distribution of matter across the cosmos. Here is the stunning part. Those frozen ripples have a specific size. Because the sound waves traveled at a known speed through matter with known properties for a known amount of time, the distance between the crests is fixed. It works out to about 500 million light-years. That 500 million light-year scale is stamped repeatedly across the entire observable universe like a cosmic ruler. When astronomers survey thousands of galaxies, they find that galaxies cluster more strongly at distances that are multiples of that scale. The pattern is everywhere. It is one of the most powerful tools in all of cosmology. It also sets a hard ceiling on how big structures can get. The sound wave crests marked zones of slightly higher density, and gravity amplified those zones into the galaxy clusters and filaments we see today. But the physics of how gravity works, combined with how long the universe has existed, limits how large any single connected structure can grow. The theoretical maximum size for any structure in the observable universe works out to about 1.2 billion light-years. That number is important. Write it down mentally, 1.2 billion light-years, because the next structures we need to talk about are larger than that. One of them is barely bigger. One of them is almost 3 times bigger. And one of them is nearly 8 times bigger. All of them exist in a universe where they should not be possible. The first of these was found not by a famous institution, but by a graduate student staring at a sky map in an office in northern England. In January of 2024, a PhD student named Alexia Lopez stood in front of a room full of professional astronomers at the American Astronomical Society meeting and showed them something that had no right to exist. A ring of galaxies, roughly circular in shape, positioned in the sky about 9 billion light-years from Earth. Its diameter, 1.3 billion light-years. Its circumference, about 4 billion light-years. Scientists immediately called it the Big Ring, 1.3 billion light-years in diameter. The theoretical maximum for any structure in the universe is 1.2 billion light-years across. The Big Ring is larger than the maximum. According to the physics of how matter clusters over cosmic time, it should be impossible. The universe simply has not had enough time, and gravity does not work at sufficient distances to organize matter into a ring that size. But there it was in the data. Lopez found it using a technique that tracks a specific type of galaxy, one that absorbs light from objects behind it in a very distinctive way, leaving a chemical fingerprint in the light spectrum. By mapping thousands of these galaxies and their distances, she could trace where matter was concentrated in 3 dimensions. The ring appeared not as a flat circle, but as a coiling, corkscrew shape in 3 dimensions, like a spring viewed edge-on, that only appears ring-shaped from our viewing angle. That is suspicious, because a structure that happens to face Earth directly is far more likely to be noticed than one tilted away from us, which means there could be others we simply cannot detect because of their orientation. The ring passed statistical testing. Lopez ran the numbers on whether a structure this large could appear by random chance in the data she was analyzing. The probability was low enough to rule out coincidence at a meaningful level. This was not noise. This was a real concentration of galaxies arranged in a shape that standard cosmological models have no mechanism to produce. Lopez herself was careful about what conclusions to draw. She did not claim the standard model was broken. She described the ring as a challenge, something that demands explanation, something that sits uncomfortably outside what current theory predicts. But she also said something striking. The sizes and shapes of these structures, and the fact that they exist right next to each other in the sky, must be telling us something important. She just didn't know what. A few theories floated around immediately after the discovery. One involved a phenomenon called baryon acoustic oscillations, the frozen sound waves from the early universe. If the Big Ring is somehow the imprint of one of those ancient waves, it would fit neatly into existing physics. The problem is that the geometry does not quite match. Baryon acoustic oscillation features are expected to appear as spherical shells of slightly higher galaxy density, not tight rings with the proportions the Big Ring shows. Another idea involved something far stranger: cosmic strings, cracks in the fabric of space itself, left over from phase transitions in the very early universe. Cosmic strings could theoretically organize matter along their length and leave ring-shaped imprints when they pass through a region of space. Physicists have discussed cosmic strings for decades, but never confirmed their existence. What made the Big Ring even more unsettling was that Lopez had already found something else in the same patch of sky, 3 years earlier, something even bigger. In 2021, while still a PhD student, Alexia Lopez found something enormous in the same region of the sky where she would later discover the Big Ring. She called it the Giant Arc, a curved structure of galaxies, groups, and galaxy clusters, sweeping across the sky like a brushstroke, located roughly 9.5 billion light-years away. Its length, 3.3 billion light-years. For comparison, the theoretical maximum size of any structure in the universe is 1.2 billion light-years. The giant arc is almost 3 times that size. It is nearly 3 times the width of a structure that should be impossible to begin with. Think of it this way. Imagine someone told you no building on Earth can be taller than the Empire State Building. That is the agreed physical limit, and every engineer and architect accepts it. Then, someone finds a building 2.5 times taller just sitting there in the middle of a normal city. That is roughly the situation astronomers found themselves in. The arc is shaped exactly as its name suggests. It sweeps in a curved line across a section of the sky that, when scaled to actual 3-dimensional space, spans an enormous swath of the observable universe. It is the arc of what might be an even larger circle, though its full extent cannot yet be determined. Some researchers have speculated that the giant arc and the Big Ring may actually be parts of the same larger structure, a superstructure so vast it would dwarf even both of them individually. If true, the combined challenge to the cosmological principle becomes even more severe. Lopez found the giant arc using the same technique she would later use for the Big Ring, mapping galaxies that absorb background light in a specific chemical pattern, creating a 3-dimensional picture of where matter was concentrated at that distance. The arc stood out clearly in the data. It was not a subtle signal hiding in noise. It was obvious once you knew what to look for. The scientific response was cautious. Many researchers argued that such structures might still fit within the standard cosmological model if you account for rare statistical fluctuations. The universe is vast. Rare things happen. Maybe these are just the outliers on the far end of a normal distribution. Strange, but not impossible. Lopez acknowledged that perspective. She did not declare victory over physics. What she said was that finding 2 such structures in the same patch of sky, at the same cosmic distance, raises the probability of a real problem far beyond what either structure does on its own. Cosmologists calculate that within the entire observable universe, you might expect to find one structure as extreme as the giant arc due to pure chance. Finding 2 in the same neighborhood is a very different statistical situation. That word, neighborhood, is worth pausing on. Both the giant arc and the Big Ring sit at almost exactly the same distance from Earth, around 9 billion light-years away. In the enormous scale of the observable universe, that makes them essentially next-door neighbors. 2 structures that individually stretch the limits of what physics allows, sitting side by side in the same cosmic region. This is either an extraordinary coincidence or a signal. And the more you look at what came before these discoveries, the more the signal starts to look like a pattern. A pattern that, if you follow it to its conclusion, leads to something so extreme that even the scientists who found it struggled to describe its scale. When Alexia Lopez presented the Big Ring at that January 2024 conference, the room understood immediately what made the discovery more than just a single anomaly. The giant arc, which she had found 3 years earlier, sits at the same cosmic distance, same region of sky, same rough neighborhood of the universe, 9 to 10 billion light-years from Earth. 2 structures that each individually violate the theoretical size limit, and they are essentially adjacent to each other in space. In science, a single outlier gets a skeptical look. 2 outliers in the same place start to look like evidence of something systematic. Cosmologists calculate that in the entire observable universe, which is a sphere about 93 billion light-years across, you would expect to find maybe one structure as extreme as the giant arc. If the standard model is correct, the probability of randomly finding 2 positioned in the same cosmic neighborhood is dramatically lower than finding 1. Lopez put the combined significance plainly. From current cosmological theories, we didn't think structures on this scale were possible. The giant arc alone was almost 3 times over the theoretical limit. The big ring exceeded it too. Having both in the same part of the sky, she said, must be telling us something important. What exactly? That question has no clean answer yet, but researchers have proposed several directions. One possibility is that both structures are part of something even larger. The giant arc is shaped like the arc of a circle. The big ring is, as its name suggests, a ring. Some scientists have noticed that the arc could plausibly be a continuation of the ring, that if you extended the arc, it curves around in a way that traces the outer edge of a massive sphere surrounding the ring. If that is true, the two structures are not just neighbors. They are pieces of a single object far bigger than either one alone, an object that would be so large it would reduce every previous size violation to a footnote. Another possibility is that both structures share a common cause, some physical process that operated in that region of the universe and organized matter in ways the standard model does not account for. Cosmic strings, those theoretical cracks in the fabric of space-time from the universe's earliest moments, could potentially leave imprints of this kind. A cosmic string passing through a region of space would sweep matter along its path, creating elongated or ring-shaped concentrations of galaxies. No cosmic string has ever been directly confirmed to exist, but the shapes of the giant arc and the big ring are exactly what some theorists predict a cosmic string's passage would leave behind. A third possibility is the most unsettling. Maybe the cosmological principle is simply wrong in this region of space. Maybe the universe is not as smooth and even at large scales as we assumed. Maybe there are places where matter is organized in ways that our current model cannot explain, not because of any single exotic cause, but because the model itself is missing something fundamental. The jury is genuinely out. No consensus exists. What does exist is a growing list of structures that each individually require explanation and together require a conversation about whether the foundation of modern cosmology is solid. That list is longer than most people realize. The giant arc and the big ring are not the first giant structures found in the universe. They are just the most recent additions to a collection of anomalies that stretches back decades. And at the top of that collection sits something that makes both of them look small. Before we reach the biggest structure ever found, it helps to fully understand the rule it appears to break. The cosmological principle sounds like abstract philosophy, but it has extremely concrete consequences. Everything in our scientific model of the universe, from how we measure the expansion rate to how we estimate the age of the cosmos, rests on it. The principle has two parts. The first is called isotropy. The universe looks the same in every direction you point your telescope. The second is called homogeneity. The universe has the same average density of matter everywhere. Together, these two properties mean that no place in the universe is special. There is no center. There is no edge. There is no region that is fundamentally different from any other region when viewed at large enough scales. This is sometimes called the Copernican principle, named after the astronomer who first moved Earth out of the center of the cosmos. For the cosmological principle to hold, matter must stop clumping at large enough scales. Zoom in close, and yes, you see galaxies, clusters, filaments, giant walls of matter, and vast empty voids. The cosmos looks lumpy up close, but zoom out past 1 billion light years or so, and the lumpiness should average out. The universe at that zoom level should look like a smooth, even distribution of matter, the same in all directions, with no oversized structures sticking out. The size limit for structures, around 1.2 billion light years, comes directly from this principle, combined with the physics of gravity and the age of the universe. Gravity pulls matter together, but it has only had a certain amount of time to work. It can only pull matter over a certain distance in that time. Any structure bigger than the pull gravity can manage in the universe's lifetime should not exist. The math is not debatable. The physics is solid. One physicist described the stakes of violating this principle. It is the second most fundamental assumption in the field, sitting just below Einstein's general relativity. Without it, most statistical tests for cosmological models break down entirely. The tools scientists use to check whether their theories match observations are built on this assumption. If the assumption is wrong, those tests stop working. The entire method of comparing theory to data gets compromised. And yet, the giant arc is almost 3 times over the limit. The Big Ring is over the limit, and both of them look modest compared to what was already in the catalogue. Before James Webb, before the Big Ring, before the giant arc, astronomers had already found a collection of enormous structures that individually strained the principle. The Sloan Great Wall, found in 2003, stretched over 1.4 billion light-years. The huge large quasar group, found in 2012, measured about 4 billion light-years across and consisted of 73 quasars. Both violated the theoretical limit. Both generated debate. Neither generated consensus on whether the standard model needed revision. Scientists argued that these structures were statistical flukes, outliers in a distribution that was otherwise well behaved. With enough galaxies, in enough sky surveys, you expect some extreme clustering just by chance. The standard model could accommodate a few outliers. That accommodation is becoming harder to sustain. Every new survey adds to the list. Every new telescope finds something else that should not be there. And none of these instruments have yet found what was detected a decade ago, hiding behind a storm of gamma rays. In early November of 2013, a team of astronomers, led by researchers in Hungary and the United States, announced something almost too large to describe. They had found a structure in the observable universe that stretched approximately 10 billion light-years in its longest dimension. They called it the Hercules Corona Borealis Great Wall, named after the constellations in the direction it lies. The theoretical maximum size for any structure, based on the cosmological principle, is 1.2 billion light-years. This structure is nearly 8 times larger than that maximum. It spans roughly 1/10 of the entire observable universe from end to end. To understand how staggering that scale is, consider that the Milky Way is about 100,000 light-years across. The distance from the Milky Way to the Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years. The distance across our entire local group of galaxies is about 10 million light-years. The Hercules Corona Borealis Great Wall is 10 billion light-years long. You could stack the Milky Way end to end 100,000 times and still not reach across it. But here is the truly strange part. Nobody has ever seen it. No photograph of it exists. No telescope image captures it. It has never been directly observed in the way you might photograph a galaxy cluster or a nebula. It was detected through an indirect signal, gamma-ray bursts. Gamma-ray bursts are the most powerful explosions in the known universe. They occur when massive stars die in certain types of supernova explosions, or when two neutron stars collide. For a fraction of a second to a few minutes, a gamma-ray burst releases more energy than the sun will produce across its entire 10 billion year lifetime. They flash from random directions in the sky, and because they are associated with regions of intense star formation, their distribution traces where large concentrations of matter exist. The team mapped 283 gamma-ray bursts and measured their distances using redshift data. They found a striking concentration of bursts in a large region of sky, a clustering that was statistically too tight to be random. The most natural explanation for that clustering was an enormous concentration of matter in that region, matter dense enough to produce far more massive stars and therefore far more gamma-ray bursts than a smooth, even distribution of matter would generate. That concentration of matter is what they called the Great Wall. It was found not by photographing it, but by listening to the deaths of its stars. The bursts are the beacons, and the wall is the darkness between them that their deaths illuminate. The physics problem this creates is severe. A structure this large implies that matter was organized on this scale at some point in the universe's past. Given how the universe expands, and how gravity operates. Organizing matter over 10 billion light years would have required either an extraordinarily long time, longer than the universe has existed, or some mechanism we have not yet identified. The team that found it acknowledged both that the structure appears real based on statistical analysis, and that they have no satisfying explanation for how it formed. Some scientists remain skeptical. They argue the clustering could be a selection effect, a bias in which gamma-ray bursts get detected, or a coincidence in how the data was collected. Others take it seriously as a real feature of the universe. The debate is still open, but the fact that it is debated at all means something. The Hercules Corona Borealis Great Wall is either a genuine structure 8 times larger than physics allows, or it is a spectacular illusion created by the limits of our instruments. Either way, the universe is forcing us to ask questions we do not have answers for, and the tool that may finally give us those answers is not a gamma-ray detector pointed at dying stars. It is a gold-plated mirror aimed at the oldest light in the universe. The Hercules Corona Borealis Great Wall was found using one of the most dramatic tools in all of astronomy, gamma-ray bursts. To understand why this matters, and why it is the only way to detect a structure that spans a tenth of the observable universe, you need to understand what gamma-ray bursts actually are. When a star many times more massive than our Sun exhausts its nuclear fuel, it collapses under its own gravity in a fraction of a second. The core implosion generates a rebound shockwave that tears the star apart in an explosion called a supernova. For the most massive stars, the collapse is so extreme that the core becomes a black hole almost instantly. As matter spirals into that newborn black hole at near light speed, 2 jets of pure energy are launched in opposite directions along the star's rotational axis, screaming outward at close to the speed of light. Those jets are gamma-ray bursts. For a few seconds to a few minutes, a single gamma-ray burst outshines its entire host galaxy, and sometimes outshines the combined light of billions of galaxies put together. The energy released in those moments is so extreme that scientists still argue about the exact physics involved. They are the universe's loudest events, because gamma-ray bursts require extremely massive stars, and because massive stars form preferentially in regions dense with gas and young stellar nurseries, their distribution across the sky traces where matter is concentrated. Dense regions of the universe produce more massive stars, which live fast and die violently, generating more gamma-ray bursts. Sparse regions produce fewer. This makes gamma-ray bursts markers of matter density, cosmic flares that light up wherever the universe has packed its material together. The team that discovered the Hercules Corona Borealis Great Wall, led by the Hungarian-American astronomer István Horváth, mapped the sky positions and distances of hundreds of these bursts and found a patch of sky where they were dramatically overrepresented. Translated into physical terms, that overrepresentation meant a huge volume of space in that direction contained far more matter than the surrounding regions. The wall is the matter, the gamma-ray bursts are the evidence. This indirect detection method is both the strength and the weakness of the discovery. Its strength is that gamma-ray bursts can be detected across essentially any distance in the observable universe, far beyond where individual galaxies can be mapped in detail. Its weakness is that gamma-ray bursts are rare and difficult to distribute evenly across the sky for statistical purposes. Some sky regions have been observed more frequently than others. Some instruments have different sensitivities in different directions. These biases could potentially create the appearance of clustering where none truly exists. The team has updated their analysis multiple times with larger datasets. Each update has been consistent with the original finding. Using over 500 gamma-ray bursts, the overdensity in the Hercules and Corona Borealis region of the sky remained statistically robust. But the debate continues, because the structure is so extreme, so far beyond what any theory predicts, that extraordinary evidence is required. One researcher working on the problem summarized it simply: the jury is still out on what it all means. That honest uncertainty is important. Science does not claim certainty it has not earned. What it does claim is that the evidence for this structure is strong enough to take seriously, strong enough to demand explanation, and strong enough to keep the scientific community actively debating it years after the initial discovery. That debate, in a very real sense, defines where cosmology stands today. And standing right in the middle of that debate is the telescope that was supposed to answer questions, not multiply them. When James Webb began sending data back in the summer of 2022, astronomers expected surprises. Every new telescope in history has found things no one predicted. Webb was supposed to reveal faint, distant, early galaxies in more detail than ever before, confirm or refine existing theories, and push the frontier of knowledge outward. What it was not supposed to do was immediately generate a crisis. Within weeks of its first science images, researchers started noticing the problem. Galaxy candidates from the very early universe, just a few 100 million years after the Big Bang, were appearing in Webb's data that looked too big, too bright, and too organized. The standard model of cosmology had very specific predictions for what early galaxies should look like: small, irregular, faint, just beginning to gather mass. What Webb was showing looked like the opposite. Scientists have a name for what Webb found: impossible galaxies. That is not a technical term, but it accurately captured the early reaction. These were galaxies comparable in stellar mass to the modern Milky Way, sitting in the universe's infancy, in an era when the universe was supposed to contain nothing but small, clumpy proto-galaxies still in the process of their first chaotic growth spurts. To understand why this was a crisis, remember how galaxies are supposed to form. Dark matter halos collapse first. They start small and merge gradually over billions of years into larger halos. As they grow, gas falls in and forms stars. The galaxy inside the halo grows roughly in step with the halo. At early times, halos are small. Galaxies should be small. The math predicts this with great precision. What Webb showed was that somehow, in the era when halos should have been small, some galaxies were already massive. The ratio of stars to the available dark matter halos was wrong. In some cases, it appeared as if these early galaxies would have needed to convert nearly all of the available gas inside their halos into stars with nearly perfect efficiency. That almost never happens in the modern universe. Star formation is inefficient. Gas gets blown out by supernovae and radiation. Most of the gas in a galaxy never becomes stars. One cosmologist described it using a vivid comparison. The standard model predicts something like scattered lights in a rural area with few clusters. Webb was showing something like the dense clustering of city lights. Far too concentrated, far too early. Astronomers immediately began debating whether the problem was real or a measurement artifact. Maybe the early galaxies only appeared bright because they contained extreme bursts of star formation that temporarily inflated their luminosity. Maybe the mass estimates were off because the tools used to estimate stellar mass from light had been calibrated on older, nearby galaxies and did not translate correctly to these early, chemically primitive ones. These were reasonable explanations. Scientists dug into them, but the more data Webb collected, the harder it became to dismiss the problem entirely. Spectroscopic follow-up, which measures precise distances and physical properties directly instead of estimating them from images, confirmed the existence and distances of many of these early massive galaxies. Some of the impossible galaxies survived scrutiny. The crisis had moved from maybe to almost certainly something is wrong with our picture of early galaxy formation. What remained deeply unclear was whether that something was a small correction to an otherwise good model, or a signal pointing toward entirely new physics. To get at the answer, astronomers needed to see not just individual galaxies, but the full large-scale structure of the early universe. They needed a map to truly understand what is going wrong with the standard model. You cannot just look at individual strange galaxies. You need to see the pattern across the whole cosmic web. You need a map, not a snapshot. In May of 2026, a team of researchers released exactly that. The largest, most detailed map of the universe ever made, built entirely from James Webb Space Telescope data. The project is called Cosmos Webb. It is the largest survey ever conducted with Webb, covering a patch of sky that holds an almost incomprehensible amount of history. The final catalogue contains nearly 800,000 galaxies, spanning almost all of cosmic time. The team traced the cosmic web, the enormous skeleton of dark matter filaments and galaxy clusters and voids that organizes all visible matter in the universe, back to when the universe was only about 1 billion years old. The lead researcher on the study, a graduate student named Hossein Hatamnia from the University of California, described the result directly. For the first time, he said, scientists could study how galaxies evolve in the cosmic web's clusters and filaments across essentially all of observable cosmic history, from the universe's infancy to the present day. What does that map look like? Imagine a vast three-dimensional web stretching from here to the edge of the observable universe. Bright nodes where filaments intersect. These are galaxy clusters, containing thousands of galaxies compressed by gravity into dense knots. Stretching between the nodes, long filaments of matter like glowing threads, each one containing galaxies, lined up along the invisible dark matter spine beneath them, and between all of it, voids. Enormous, nearly empty bubbles of space where almost nothing lives, taking up about 80% of the universe's volume while containing only about 20% of its mass. The Cosmos Webb map revealed this structure in a level of detail that Hubble Space Telescope data of the same region could not approach. The researchers ran direct comparisons. Structures that Hubble blurred into indistinct smears resolved under Webb's sharper eye into clearly separated galaxy clusters and distinct filaments. The researcher who led the team's scientific analysis described the jump in depth and resolution as truly significant. But the map did more than show pretty structure. It confirmed and expanded the findings about where galaxies form and what happens to them based on their environment. Galaxies living in dense filaments and clusters deep inside the web behave differently from galaxies floating in the voids between filaments. They form stars at different rates. They reach the end of active star formation, what astronomers call quenching, at different times. The environment inside the cosmic web actively shapes the life cycle of every galaxy within it. That finding carries a striking implication. Webb's map has shown that the cosmic web, this skeleton of invisible dark matter, is not just the backdrop of the universe. It is an active participant in how galaxies live and die. The structure of the universe affects the objects within it, which means that to understand galaxies, you must understand the web itself. And understanding the web means confronting the question of whether the web was supposed to look like this. Whether the structures Webb is mapping at early times are consistent with what the standard model predicts, or whether they reveal something the standard model cannot account for. The Cosmos Webb map is the most powerful dataset yet for testing that question, and the question is far from settled. What makes that uncertainty deeper is a tension that runs through all of modern cosmology. A disagreement between two measurements of the universe so stubborn that physicists have been arguing about it for years, and Webb has only made it sharper. There is a number that sits at the center of all modern cosmology. It describes how fast the universe is expanding right now. Every cubic megaparsec of space, roughly every 3 million light-years in every direction, is growing by a specific number of kilometers per second. Get that number right, and you can calculate the age of the universe, the fate of the universe, the amount of dark energy driving the expansion, and much more. Scientists call it the Hubble constant, named after the astronomer Edwin Hubble, who first measured cosmic expansion in the 1920s. The problem is that the two best methods for measuring this number give different answers. and they agree with themselves so well, internally, that the disagreement cannot be explained by measurement error. This is known as the Hubble tension, and it has kept cosmologists awake for years. Method 1 looks at the early universe. Scientists study the cosmic microwave background, that ancient light left over from when the universe was 400,000 years old, and use it to measure the Hubble constant. The result, from the Planck satellite's ultra-precise measurements, is about 67 kilometers per second for every 3.3 million light-years of space. Method 2 looks at the nearby universe. Scientists measure distances to galaxies using stars called Cepheid variables, and a type of stellar explosion called a Type 1a supernova. Both serve as extremely reliable distance markers. When researchers use these local measurements to calculate the expansion rate, they consistently get about 73 kilometers per second for every 3.3 million light-years of space. 67 versus 73. That gap sounds small. In cosmology, it is enormous. The two measurements use completely different tools, completely different assumptions, and completely different regions of the universe. They have been checked, rechecked, and checked again. The gap has not gone away. If anything, it has grown more stubborn as measurements have become more precise. The disagreement now exceeds 5 standard deviations of statistical certainty, a threshold that physicists typically consider a discovery in any other context. James Webb was supposed to help resolve this. Hubble, the old space telescope, measured those local Cepheid and supernova distances, but critics wondered whether Hubble's resolution was blurring stars together and introducing errors. Webb's sharper optics would check the same measurements with far greater precision. Initial results from Webb confirmed the local measurements. The expansion rate in the nearby universe really does appear to be faster than what the early universe predicts. Both answers cannot be right simultaneously if the standard model of cosmology is correct. Either the early universe measurements are wrong, or the local measurements are wrong, or the standard model itself is missing something. Some physicists believe the resolution is an exotic ingredient called early dark energy, a form of energy that existed briefly in the very young universe, changed the physics of the early cosmos just enough to shift the predicted expansion rate, and then vanished, leaving no trace except its effect on that number. Early dark energy has another attractive property. It might also explain why Webb is finding massive galaxies too early. If the young universe had this extra energy, briefly boosting structure formation, galaxies could have grown faster than the standard model predicts. This single proposed ingredient, early dark energy, could potentially stitch together two of the biggest mysteries Webb has created. The impossible galaxies and the Hubble tension might both be symptoms of the same missing physics. Understanding what that physics is would rewrite textbooks from the Big Bang through to today, and sitting underneath all of it, potentially connecting the impossible structures, the Hubble tension, and the early massive galaxies, is a component of the universe that controls everything but cannot be seen, touched, or directly detected by any instrument ever built. The universe is not just expanding, it is accelerating. Galaxies are flying apart from each other faster and faster over time, not slowing down the way gravity should cause them to. This discovery earned 3 scientists the Nobel Prize in Physics in 2011, and it introduced one of the most disturbing facts in all of science. Something is pushing the universe apart, and we have absolutely no idea what it is. Scientists call it dark energy. The name is deliberately vague because we genuinely do not know what dark energy is. We know it exists because the expansion of the universe tells us it must exist. We know it makes up roughly 68% of the total energy content of the universe. We know it is uniform, spread evenly through all of space, and that it appears to act like a constant outward pressure pushing against gravity. We do not know what produces it, where it comes from, or whether it is truly constant or slowly changing over time. We do not have a single particle detector that can detect it. We cannot produce it in a laboratory. Its existence is inferred entirely from what it does to the universe's expansion. The standard cosmological model treats dark energy as a fixed constant, a kind of energy built into the fabric of space itself. Every cubic inch of space contains the same amount of dark energy, and as space expands, more space is created, which means more dark energy, which means faster expansion. The model fits most observations extremely well, but Webb and other recent telescopes have introduced some unease about whether dark energy is truly constant. If it is slowly changing over time, the standard model's predictions about cosmic expansion would need to be revised. That revision could ripple through everything: the age of the universe, the size of the observable universe, the predicted distribution of galaxy clusters. All of these depend on how dark energy behaved across cosmic history. The connection to the impossible structures is subtle but real. If dark energy is not constant, if it was slightly different in the early universe, then the rate at which matter clustered and grew would have been different too. Structures might have organized on larger scales than the standard model predicts, or organized more quickly. The Big Ring, the Giant Arc, the Hercules Corona Borealis Great Wall, all of them might be less impossible in a universe where dark energy has been evolving rather than sitting fixed. This is speculative. The data on dark energy's constancy is still being gathered. The Euclid Space Telescope, launched by the European Space Agency in 2023, was specifically designed to measure dark energy's behavior over cosmic time with unprecedented precision. The Roman Space Telescope being built by NASA will add to that measurement. Together, they are designed to find out whether dark energy is truly constant or has been quietly evolving across billions of years of cosmic history. If it has been changing, physics gets rewritten. If it has been constant and the impossible structures are still there, physics also gets rewritten, just differently. Either way, rewriting is coming. The only question is how much. And sitting underneath all the exotic physics, connected to both dark energy and the impossible structures, is a phenomenon stranger than anything discovered so far. A phenomenon that suggests space itself may have a kind of memory of its earliest moments. Imagine the universe a fraction of a second after the Big Bang. Space is unimaginably hot, packed with energy beyond anything that exists today. As the universe cools over the following fractions of a second, it goes through phase transitions, moments when the physical properties of space itself change state, similar to the way water turns to ice when temperature drops past a threshold. In ordinary water freezing into ice, the process does not happen perfectly uniformly across the whole glass. In some spots, ice crystals nucleate and grow. Where crystals growing from different centers meet, they do not always align perfectly. The boundary between two misaligned ice crystals is a crack, a line of structural imperfection running through the ice. Physicists call these boundaries defects. The same thing may have happened to the fabric of space itself. If the early universe went through phase transitions as it cooled, and theoretical physics suggests it almost certainly did, those transitions may have left behind structural defects in the fabric of space-time. Not in matter, not in energy, but in space itself. These defects, stretched across cosmic scales by the expansion of the universe in its first moments, are called cosmic strings. A cosmic string, if one exists, is an incredibly thin filament of energy, thinner than a proton, but stretched to lengths that could span billions of light years. The energy density packed into that thin line is almost beyond comprehension. A single section of cosmic string 1 mile long would weigh about as much as Earth. Its gravitational influence on surrounding matter would be immense. Galaxies and gas would be drawn toward it, organizing into sheets and filaments along its length. Theoretical physicists have studied cosmic strings for decades. They appear naturally in several leading theories of the early universe, including string theory and certain models of inflation, the period of explosive expansion right after the Big Bang, but no cosmic string has ever been directly detected. Their existence remains a prediction, not a confirmed fact. Astronomers have looked for their gravitational fingerprints in the cosmic microwave background and in the bending of light from distant galaxies. The evidence so far is inconclusive, but the Big Ring and the giant arc have given cosmic string theorists new reason for interest. The shapes of both structures are potentially consistent with what a cosmic string sweeping through space might leave behind. A string passing through a region could organize matter along its path, and as the string moves or oscillates, it could create ring-shaped or arc-shaped concentrations of galaxies. The geometry is not a perfect match to the simplest cosmic string predictions, but it is not ruled out either. If cosmic strings turn out to be real, and if they are the explanation for the Big Ring and the giant arc, the discovery would be one of the most important in the history of physics. It would be the first direct evidence of a phase transition in the fabric of space itself. It would confirm theoretical predictions that have been sitting unverified for 40 years. And it would mean that the universe carries physical scars from its earliest moments, ancient wounds in the structure of space that have been shaping the distribution of galaxies across billions of years without anyone knowing. That possibility, the universe scarred from birth, organizing matter along its wounds, is one of the most extraordinary ideas in science, and the machine that is best positioned to find the evidence for or against it is the same machine that found the impossible galaxies and mapped 800,000 galaxies in a single survey. In May of 2026, the full results of the Cosmos Webb survey were released to the public. It is the single most ambitious observation campaign ever conducted with James Webb, and the map it produced is unlike anything that existed before. Zoom in on that map and you see galaxies by the thousands, each one a city of hundreds of billions of stars, each one sitting at a specific location in the cosmic web's architecture. Zoom out and you see the filaments connecting them, long, bright threads of matter stretching across hundreds of millions of light years. Zoom out further and you see the nodes where filaments meet, dense knots of galaxy clusters glowing bright in the map, and between all of it, dark, empty, the voids. The map goes back nearly 13 billion years in cosmic time. The left edge represents the universe as it exists today. The right edge shows the universe when it was barely a billion years old. Moving from one end to the other, you are watching the universe age in a single image, and the aging is dramatic. In the early universe end of the map, the cosmic web is there, but it is rougher, less organized. Filaments are thinner and less well-defined. Clusters are less massive. The structure has not had time to settle into the smooth, organized architecture it shows in the nearby universe. But it is already there, already forming, already organizing matter into the web that will eventually look like what we see around us today. This is both expected and deeply informative. The cosmic web should have started forming within the first few 100 million years after the Big Bang, as dark matter halos merged and pulled ordinary matter along with them. Seeing it appear in Webb's data at the 1 billion year mark confirms that general picture, but the details of how that early web is organized, how many clusters exist, how massive they are, how thickly the filaments are packed, those details are critical tests of the standard model. And in some of those details, the standard model struggles. The Cosmos Webb team found that some regions of the early universe already show a level of structure that is more developed than simulations predict. Certain filaments are more pronounced, certain clusters more massive, at times when the standard model says they should still be in earlier stages of assembly. This is the same broad signature seen in the impossible galaxies, but now extended across the full cosmic web. The problem is not just individual oversized galaxies, it is the overall pace of structure formation. The map also revealed something about how galaxies die. As galaxies fall into the denser environments of clusters and thick filaments, they stop forming new stars far more rapidly than galaxies floating in the voids between filaments. The environment of the cosmic web actively strangles star formation. Dense regions kill galaxies faster. The peak of cosmic star formation happened billions of years ago, and the Cosmos Web map shows exactly how the web's growth contributed to winding it down. The universe's most creative era is behind it. The web that James Webb mapped is, in some ways, a record of a fire going out. The most stars that will ever exist in the universe already exist. No new explosion of galaxy formation is coming. The universe is slowly, over billions of years, dimming. That cosmic dimming is partly driven by the same structures that are challenging the Standard Model. And the more Webb reveals about those structures, the clearer it becomes that the Standard Model is missing something. What that something is remains the defining question of modern cosmology. And the answer, if it exists, may require us to accept that space itself behaves in ways we have never accounted for. Picture a hospital nursery. Every newborn in that room is small, fragile, and hours old. Now imagine walking in and finding a full-grown adult sitting in one of the cribs. That is roughly the situation James Webb created for cosmologists when it began photographing the early universe. The Standard Model of galaxy formation is precise. It makes specific predictions about what galaxies should look like at different ages of the universe. In the first 500 million years after the Big Bang, galaxies should be small, irregular, chaotic. They are supposed to be in the earliest stages of assembly, with dark matter halos still growing, gas still falling in, star formation just beginning to ramp up. Mass takes time to build. Billions of years of merging and accumulating. You cannot rush it. Webb rushed it. In some of the earliest snapshots of the universe that Webb has captured, representing times when the universe was between 300 and 600 million years old, researchers found galaxies with stellar masses comparable to the modern Milky Way. The Milky Way contains somewhere between 100 and 400 billion stars and took roughly 13 billion years to accumulate that mass. These early galaxies appeared to have achieved comparable mass in a tiny fraction of that time. One astronomer described the problem with a vivid image. The Standard Model predicts that the earliest galaxies should be scattered and faint, like lights in a rural area far from any city. What Webb was showing looked like the dense cluster of light above a major metropolitan area. Too much light, too concentrated, way too early. The technical issue runs deeper than just size. To build that much stellar mass so quickly, those early galaxies would have needed to convert gas into stars with almost perfect efficiency. In the modern universe, star formation is messy and wasteful. Radiation from newborn stars blows gas out of the galaxy before it can collapse into stars. Supernova explosions scatter material. Black holes at galactic centers pump out enough energy to suppress star formation entirely. As a result, galaxies typically convert only a small fraction of their available gas into stars at any given time. The early impossibly massive galaxies appear to have done something different. Some researchers estimate that certain of them would have needed to turn essentially all of their available gas into stars with almost no waste. One team described the required efficiency as approaching 100%, a figure that has no precedent in any galaxy we observe nearby. Multiple explanations have been proposed. One is that these galaxies went through extreme but brief bursts of star formation, flaring brilliantly for a short time before settling down. If measured at the moment of peak burst, they would appear far more massive and luminous than their average state over time. This explanation has some support. Simulations show that early galaxies may have formed stars in intense pulses rather than at steady rates, and those pulses would make the galaxies look far bigger than the standard smooth formation model predicts. Another explanation is that early dark energy, the mysterious brief force some physicists believe existed in the young universe, accelerated the pace of structure formation. If the young universe had a brief extra boost of energy, gravity would have pulled matter together faster, halos would have grown bigger sooner, and galaxies inside them could have assembled more mass in less time. Neither explanation fully resolves the tension, and both point to the same uncomfortable conclusion. The early universe was forming things faster than the universe was supposed to be able to. Faster. bigger, earlier. The pattern keeps repeating, and the next piece of that pattern involves not just how galaxies formed, but what existed before any galaxy did. Before any galaxy, before any solar system, before any planet, there were stars. The very first stars in the universe burned under conditions so extreme that nothing like them exists anywhere in the cosmos today. Astronomers call them population 3 stars. They have never been directly observed. They are predicted by theory, confirmed by their absence in ancient galaxies, and hunted by James Webb with more determination than perhaps any other target in the universe. Here is what made them different. The early universe contained almost no elements heavier than hydrogen and helium. Heavier elements, carbon, oxygen, iron, silicon, the building blocks of planets and living things, are forged inside stars and scattered into space when those stars die. In the beginning, none of that had happened yet. The first stars formed from pure hydrogen and helium, the raw output of the Big Bang itself. Stars made only of hydrogen and helium behave very differently from the stars alive today. Without heavier elements, the gas clouds that form stars cannot cool down as efficiently. Hot gas resists collapse. So the first clouds of hydrogen needed to gather far more mass before gravity could overcome the pressure and ignite nuclear fusion. The result was stars of extraordinary size, many of them tens or even hundreds of times more massive than our Sun. Some theoretical models suggest the most extreme population 3 stars could have been over 1,000 times the Sun's mass, making them the largest stars that will ever exist at any point in the history of the universe. These giants burned with a ferocity our Sun cannot match. They were so hot that they blazed in ultraviolet light, far beyond what human eyes can see, and they burned through their fuel so fast that they lived for only a few million years before dying in catastrophic explosions. For comparison, our Sun is expected to live about 10 billion years. These stars lived and died in the time it takes Earth to orbit the Sun a few million times. When they died, they scattered the first heavy elements into the surrounding gas, seeding the universe with the raw materials for everything that followed. Every carbon atom in your body, every oxygen atom in the water you drink, was forged in the core of a star and scattered into space by its death. The population, 3 stars, were the first to start that process. They were the universe's original manufacturers. James Webb was designed from the beginning with these stars as a primary target. The infrared light Webb detects is exactly the wavelength range where the signature of population 3 stars stretched across billions of light years of expanding space would appear. In 2023, Webb captured images of a galaxy so ancient and so chemically primitive that researchers found evidence suggesting a population 3 star cluster might be visible within it, possibly the closest humanity has ever come to seeing one of the universe's first stars directly. If Webb can confirm a direct detection of population 3 stars, it would be one of the most profound discoveries in the history of astronomy. It would close a loop running from the first moments of the Big Bang, through the deaths of those first stars, through every generation of stars that followed, all the way to the atoms inside you right now. The universe's entire chemical history written in a single observation. But population 3 stars were only the opening act of an even more dramatic transformation. What came next rewrote the entire visible universe. For the first several 100 million years after the Big Bang, the universe was dark. There were no stars, no galaxies, no visible light, just hydrogen and helium gas, slowly cooling, slowly clumping, gravity quietly doing its patient work. Astronomers call this the cosmic dark ages, and it is exactly what it sounds like. An era of complete and total darkness stretching across the entire observable universe for hundreds of millions of years. Then the first stars lit up, and what they did to the universe around them was dramatic enough to warrant its own name in the history of the cosmos. Scientists call it the epoch of reionization. To understand reionization, you need to know something about hydrogen. After the Big Bang cooled the universe enough for electrons to bond with protons and form neutral hydrogen atoms, that neutral hydrogen filled all of space. Neutral hydrogen absorbs certain wavelengths of light very effectively, particularly the ultraviolet light produced by hot, young stars. So, even after the first stars turned on, the universe was still largely opaque. The stars were shining, but the neutral hydrogen surrounding them absorbed their light before it could travel very far. As more and more stars formed, particularly those extremely hot and luminous population, 3 stars and the first young galaxies blazing with star formation, their combined ultraviolet radiation began doing something remarkable. It stripped electrons from the surrounding hydrogen atoms, converting the neutral hydrogen back into ionized hydrogen, a plasma of free protons and electrons. This process of stripping electrons is called ionization. The prefix Re refers to the fact that the universe had been in this ionized plasma state before, in the very early universe, before neutral atoms formed. The light from the first stars was pushing it back into that earlier condition. The reionization process started in bubbles. Around each concentration of early stars, a sphere of ionized hydrogen grew outward, like a soap bubble inflating from a tiny point. As more stars formed, more bubbles appeared. Over hundreds of millions of years, the bubbles grew and merged, overlapping, combining, until they filled the entire universe. The last patches of neutral hydrogen were ionized. The universe became fully transparent. Light could travel freely in every direction without being absorbed. This moment, when the universe became transparent for the second and final time, is one of the most important transitions in cosmic history. The universe went from a fog that blocked all vision to the clear, open void we observe today. If you had been an observer anywhere in the universe at the right moment, you would have seen the fog lift. Galaxies that had been invisible suddenly became visible. The cosmos opened its eyes. James Webb can actually observe this process happening. By looking at galaxies at the right distances, it can see how the fog of neutral hydrogen changed over time. Webb has already begun identifying the bright young galaxies responsible for driving reionization, the sources that punched holes in the cosmic fog and let the light through. Understanding which galaxies drove reionization and how quickly it happened is a crucial test of the Standard Model. And in the details, Webb is again finding that things moved faster than expected. The fog lifted earlier than the Standard Model predicted. Light escaped sooner. The universe cleared its throat faster than the timeline suggests it should have. The pattern of too fast, too early, too organized continues right through the most dramatic transformation in cosmic history. The universe will never be as alive as it was roughly 10 billion years ago. That statement is not a guess. It is a conclusion drawn from decades of observations across thousands of galaxies, and it carries a strange melancholy once you really absorb it. Star formation, the process of gas collapsing under gravity into the nuclear furnaces we call stars, reached its absolute peak when the universe was between 2 and 4 billion years old. During that era, sometimes called cosmic noon, galaxies across the universe were producing new stars at a rate roughly 10 times higher than they do today. The cosmos was in its most creative phase, a sustained explosion of stellar birth that filled galaxy after galaxy with new suns, new light, new planetary systems. The scale of it is hard to picture. Every second during cosmic noon, across all the galaxies in the observable universe combined, enough gas was collapsing into stars to produce dozens of new suns. The night sky of any planet during that era, if one had existed with the right viewing angle, would have blazed far more brightly than anything visible today. The universe was in full creative fire. James Webb can look directly at that era. Galaxies at the right distances appear to Webb as they existed during cosmic noon, and the detail Webb captures in those images is extraordinary. Star-forming regions glow in infrared. Gas clouds in the act of collapse are visible. The relationship between galaxies and the cosmic web they live in at that pivotal time is now being mapped by Cosmos Webb with a clarity that was impossible before. What Webb has confirmed about cosmic noon is troubling in the same way the early galaxy findings are troubling. The transition into peak star formation happened faster than expected. Galaxies were already producing stars at high rates earlier than the standard model predicts, which is consistent with the picture of early massive galaxies assembled too quickly. The ramp up to cosmic noon was steeper than the model can easily explain. But what has happened since cosmic noon is its own story. Since that creative peak, the rate of star formation across the universe has dropped by roughly 10 times. The universe today forms stars at a fraction of the rate it did at its height. Galaxy after galaxy has seen its star formation slow, stall, and in many cases stop entirely. Astronomers call this quenching, the extinguishing of a galaxy's star-forming activity. The Cosmos Web map showed exactly how the cosmic web participates in this quenching. Galaxies that fall into the dense environments of clusters and thick filaments lose their cold gas faster. The extreme environments of these dense nodes strip gas away from galaxies, shut off the supply of new material, and leave the galaxy unable to form new stars. The web that built galaxies also kills them. The universe's creative era is over. The fire that produced all the stars and planets and the conditions for life peaked billions of years ago and has been cooling ever since. Every star being born anywhere in the universe today is a late arrival in a party that largely ended long before Earth existed. The universe is slowly running out of the raw materials for new suns. That slow dying has a shape, and that shape, across billions of light years of space, is controlled by the same structure that James Webb has been mapping. A structure whose full scale and full strangeness is only now coming into view. 80%. That is the fraction of the universe's volume that contains almost nothing. No galaxies, no clusters, no filaments of dark matter, just vast, nearly empty bubbles of space, some stretching hundreds of millions of light years across, where the average density of matter is a tiny fraction of the cosmic average. These are the voids, and they are one of the strangest features of the universe. Voids are not simply the gaps between galaxies. They are active participants in cosmic structure, as galaxies and dark matter cluster into filaments and nodes under the pull of gravity. The regions between them empty out. Matter drains away from voids, flowing along sheets and walls toward the denser filaments and clusters. The voids expand, not just because the universe is growing, but because they are actively evacuated by the gravitational pull of the denser surrounding structures. Here is where voids become genuinely strange. The interior of a void is not just empty, it is expanding faster than the universe averages. Dark energy, the mysterious repulsive force pushing the cosmos apart, operates everywhere in space equally. But inside a void, where there is almost no matter providing gravitational resistance, dark energy faces almost no opposition. The void interior expands more quickly than the cosmic average. Voids are pockets where dark energy wins completely. This means that the distribution of voids across the universe, their sizes and shapes and how they connect to the surrounding web of filaments and walls, carries information about dark energy. A universe with different dark energy would have differently shaped voids. Mapping voids precisely is one of the most powerful ways to measure dark energy's behavior over time. The Cosmos Web survey has mapped the void distribution in the early universe with more detail than any previous instrument allowed. And the voids in the early universe look different from what the standard model predicts in subtle but important ways. They are slightly more pronounced at early times, slightly better defined than simulations suggest they should be. Again, the universe appears to have organized itself faster than it was supposed to. There is also a void right here, surprisingly close to us. The region of space containing the Milky Way sits inside what astronomers call the KBC void, named after the 3 researchers who identified it. The KBC void is roughly 2 billion light-years in diameter, making it one of the largest known voids in the observable universe. We live inside it. The existence of the KBC void has its own implications for the Hubble tension. If we sit inside an unusually large, underdense region, the local expansion rate we measure might be slightly inflated compared to the cosmic average, Because the void is evacuating around us faster than a typical region would, some researchers have proposed that the KBC void explains part of the discrepancy between the local and early universe measurements of the expansion rate. Others dispute whether the void is large enough or deep enough to account for the full gap. The universe, it turns out, is not just full of impossible structures, it is also full of impossibly large emptinesses. And the boundary between the full regions and the empty ones, the walls and sheets and filaments of the cosmic web, may themselves be telling a story about forces and events that our standard model has not yet learned to read. The evidence for that unread story has been accumulating across multiple telescopes and multiple types of observation, and now 2 new machines, built specifically to answer these questions, are being pointed at the sky. James Webb was not designed to break cosmology. It was designed to see further and more clearly than any telescope before it. The breaking happened as a consequence. Now 2 missions, built specifically to confront the breaking, are either operational or nearly ready. The first is Euclid, launched by the European Space Agency in July of 2023. Euclid sits at the same gravitational sweet spot as James Webb, 1 million miles from Earth, and its job is extraordinarily specific. It is mapping the 3-dimensional distribution of over 1 billion galaxies across roughly 1/3 of the entire sky, reaching back about 10 billion years in cosmic history. The goal is to measure dark energy's behavior over cosmic time with the highest precision ever achieved, and to measure how the cosmic web has grown and changed across those billions of years. Euclid's design reflects what scientists care most about right now. Its wide-field camera can photograph a patch of sky the size of 2 full moons with each exposure, stacking up galaxy positions and distances at a rate no pointed telescope like Webb can match. Quantity over depth. Mapping the large-scale structure requires enormous statistical samples, and Euclid is built to provide them. Early results from Euclid have already generated discussion. The first large-scale map it released showed hints of subtle differences from standard model predictions in how galaxies cluster at certain scales. Whether those hints harden into confirmed discrepancies will depend on years of continued observation and careful analysis of the full dataset. The second machine is the Nancy Grace Roman Space Telescope, built by NASA. As of mid-2026, Roman is in its final stages of preparation, with launch expected within the next year. Roman has a mirror comparable in size to Hubble, but with a field of view 100 times wider, combining the depth of a Sirius space telescope with the broad coverage needed for large-scale surveys. It will measure hundreds of millions of galaxies, look for the shapes of baryon acoustic oscillations in the distribution of matter at different cosmic epochs, and search for evidence of how dark energy has evolved. Roman was also designed with the impossible structures specifically in mind. One of its key science goals is to determine definitively whether structures like the Big Ring and the giant arc are consistent with the standard model when examined in the context of a much larger sample of the sky, or whether they represent genuine statistical anomalies that demand new physics. Both Euclid and Roman will also sharpen measurements of weak gravitational lensing, the subtle bending of light from background galaxies by the mass of foreground structures. This effect maps the distribution of all matter, dark and visible, across enormous regions of sky. It is one of the most powerful tools available for testing whether the standard model's predictions for how matter clusters match reality. The next 5 to 10 years of data from these 3 telescopes, Webb, Euclid, and Roman, working in combination, will be the most powerful test of the standard model in the history of cosmology. If the tensions and anomalies they are finding are real, those years of data will force physics to change. If the anomalies resolve away as measurement errors or statistical flukes, the standard model will emerge strengthened. Either outcome moves science forward, but those who have been watching the data accumulate are increasingly skeptical that the anomalies will simply vanish. They have a habit of getting stronger, not weaker, as the instruments improve. The standard model of cosmology, sometimes called lambda-cold dark matter after its two most important components, has been the ruling theory of the universe for about 30 years. It describes the Big Bang, the formation of the first atoms, the growth of dark matter halos, the assembly of galaxies, the expansion of space, and the large-scale structure of the cosmos. It fits an enormous range of observations with remarkable accuracy. For most of modern cosmology's history, it has been the most successful scientific model in the history of physics. Lambda refers to dark energy, represented in Einstein's equations by the Greek letter lambda, a constant term that accounts for the accelerating expansion of the universe. Cold dark matter refers to the type of dark matter the model assumes, particles that move slowly, compared to light and cluster, into halos under gravity. Together, these two components account for about 96% of the universe's total energy content, leaving only 4% as ordinary matter, everything you can see, touch, and detect. The model makes extremely precise predictions. It predicts exactly how the cosmic microwave background should look. It predicts how many galaxy clusters should exist at different epochs in cosmic history. It predicts the distribution of baryon acoustic oscillations across the sky. It predicts the rate at which structure should grow over time. In almost every case where these predictions have been tested against high-quality data, the model performs extraordinarily well, which is what makes the current situation so uncomfortable. The tensions are not appearing in the tests where the model performs well. They are appearing at the edges, in the newest data, with the most powerful instruments looking at the extremes of cosmic structure, the impossible galaxies, the oversized structures, the Hubble tension, the hints in early dark energy data. These are not trivial deviations. They are stubborn, recurring, and growing in statistical weight with each new dataset. What specifically might be missing? Physicists have several candidates. One is that dark matter is not as cold as the model assumes. If dark matter particles move faster, they would smooth out small-scale structure, preventing the formation of very small halos and changing the rate at which large halos grow. Warm dark matter, as this variant is called, would modify the timeline of galaxy formation and potentially ease some of the tension with Webb's early galaxy observations. Another candidate is a new type of dark energy that is not constant, one that changes in strength over time, or even varies from place to place in space. This would affect how the cosmic web grows at different epochs, potentially allowing larger structures to form at earlier times than the standard model allows. A third possibility involves modifications to gravity itself. General relativity is tested extremely well in the solar system and in binary pulsar systems, but on cosmic scales, it has never been tested with the same precision. If gravity behaves slightly differently across billions of light years than Einstein's equations predict, the growth of cosmic structure would be affected in ways that could explain some or all of the anomalies. Any of these modifications would require new physics. Any of them would change textbooks from the introductory level to the most advanced research. And none of them is confirmed. The data is pointing in a direction, but has not yet arrived at a destination. What it has done is eliminate the comfortable certainty that the standard model is complete. That certainty is gone. Zoom out far enough, and the universe smooths out. In theory, that is the entire basis of the cosmological principle, and there is a specific scale at which scientists predicted the smoothing would happen. Astronomers gave this transition a name that is both elegant and final: the end of greatness. The idea comes from observations made in the 1990s as larger and larger sky surveys became possible. As scientists mapped the positions of galaxies across greater volumes of space, they kept finding structure: walls, filaments, voids, superclusters. Each new survey pushed the edge of the mapped region outward, and each time, new structures appeared right at the edge of the survey volume. There was always something bigger just beyond the frontier. But eventually, the argument went, the structures had to stop. At some large enough scale, the distribution of matter would average out into uniform density. The end of greatness was the scale at which this transition was supposed to occur, estimated at several 100 million light-years. Beyond that distance, the universe should look statistically uniform in all directions. For a while, the evidence supported this picture. Galaxy surveys reaching out a few 100 million light-years seemed to confirm that matter distributed more evenly as the survey volume grew. The end of greatness appeared to be real, and the cosmological principle appeared to be holding. Then surveys got bigger. The Sloan Great Wall appeared, stretching 1.4 billion light-years. The huge large quasar group appeared at 4 billion light-years. The giant arc at 3.3 billion. The Big Ring at 1.3 billion in diameter. The Hercules Corona Borealis Great Wall at 10 billion. With each survey breakthrough, the end of greatness retreated. Every time astronomers reached what they thought was the scale of uniformity, something enormous was hiding just beyond it. The theoretical limit of 1.2 billion light-years was supposed to be the hard ceiling, the scale beyond which gravity simply cannot organize matter given the age and expansion rate of the universe. Structures beyond that size should not exist. The fact that several do, at multiple scales up to 10 billion light-years, suggests either that the cosmological principle is wrong or that it applies at a scale far larger than anything current surveys can reach. That second option is genuinely unsettling in its own way. If the universe only averages out at scales of, say, 50 billion light-years or 100 billion, then the observable universe, which is a sphere about 93 billion light-years across, would sit entirely within a region that looks lumpy. Our view would be fundamentally unrepresentative of the universe as a whole. Everything cosmology has concluded by treating the observable universe as a fair sample could be wrong. This is not a new concern. Physicists have discussed it for decades, usually setting it aside because the alternative is making cosmology untestable. If the observable universe is not a representative sample, the entire enterprise of using our observations to understand the universe as a whole breaks down. Science needs to assume it is working with a fair sample, but assumptions do not guarantee truth. The uncomfortable possibility is this: we may live in a universe so large and so structured on such enormous scales that the patch we can observe is simply too small to reveal its full nature. Everything we know about the cosmos could be correct locally and still be deeply incomplete globally. Most cosmological models assume the universe looks the same in every direction from any point within it. That is isotropy. But what if it does not? What if there is a preferred direction in the cosmos, a subtle but real asymmetry built into the large-scale structure of the universe? What if, in the most literal sense, the universe is lopsided? This idea sounds extreme. It conflicts with the most basic assumption of the cosmological principle. It would undermine decades of cosmological inference. And yet, scattered through the data, researchers keep finding hints of exactly this. The cosmic microwave background is the most detailed map of the early universe in existence. It was produced when the universe was 400,000 years old, and its temperature variations of less than 1 part in 100,000 record the seeds of all future structure. It should look statistically the same in every direction. When the Planck satellite mapped it with extraordinary precision, it mostly did, but not entirely. There is a feature in the cosmic microwave background data sometimes called the axis of evil, a somewhat dramatic name applied by researchers who found that certain large-scale patterns in the microwave background align with each other in a way that seems to prefer a particular direction in space. The dipole, quadrupole, and octupole components of the temperature map, which should be randomly oriented relative to each other, appear to align along roughly the same cosmic axis. The probability of this alignment occurring by chance in a truly isotropic universe is very low. There are also hints in galaxy surveys that the expansion rate of the universe may be slightly different in different directions, a potential violation of isotropy on the largest scales. These hints are not yet at the level of confirmed discovery, but they are persistent, appearing across different datasets and different analysis techniques. If the universe is genuinely anisotropic at large scales, the implications are radical. It would mean that the laws of physics, or at least the conditions under which they operate, are not the same everywhere. It would mean that our position in the universe is not arbitrary, but situated within a specific, large-scale structure that has a preferred direction. Every cosmological measurement made under the assumption of isotropy would need to be reinterpreted. The most exotic explanation for anisotropy involves the period of inflation, the proposed epoch of extremely rapid expansion in the first fraction of a second after the Big Bang. If inflation was not perfectly uniform, if it proceeded slightly differently in different directions, it could have left a directional imprint on the universe that persists to this day. The impossible structures, the axis of evil in the microwave background, and the directional hints in galaxy surveys might all be connected to a subtle asymmetry built into the cosmos at its birth. James Webb cannot directly test large-scale isotropy because its field of view is far too small. But the combination of Webb's deep early universe data with Euclid's wide-field galaxy surveys is designed to look for exactly these large-scale patterns. If they are real, the combined dataset should reveal them. If they vanish under scrutiny from better instruments, the standard model breathes easier. The next years will tell, and whatever the answer, it connects directly to the biggest question in cosmology. What does all of this mean for us? Every discovery discussed in this video has been about structures out there, billions of light years away, in the distant universe. But there is a possibility that has been quietly present throughout all of it. What if we ourselves are inside a structure too big to recognize from where we stand? The Milky Way sits inside the KBC void, a roughly 2 billion light-year underdense region of space named after the 3 astronomers who identified it. Inside that void sits the local group, our cluster of a few dozen galaxies, including the Milky Way and Andromeda. Beyond the local group, the nearest large galaxy cluster is the Virgo cluster, about 55 million light-years away. The Virgo cluster is part of a supercluster called Laniakea, which stretches about 500 million light-years across and contains hundreds of thousands of galaxies. Laniakea itself is a node in a larger cosmic web structure. In other words, we are not floating in empty space. We are embedded in layer upon layer of cosmic structure, each layer larger than the one before. In a hierarchy that stretches to scales, we are only now beginning to map. The largest structures we are finding, the Big Ring, the Giant Arc, the Hercules Corona Borealis Great Wall, challenge the assumption that this hierarchy ends cleanly at a scale of 1.2 billion light-years. If such structures exist at 9 billion light-years, there could be comparably enormous structures at every scale, including right here, surrounding us, too vast to see the shape of from inside. From inside a room, you cannot see the shape of the building. From inside a city, you cannot see where the city ends. From inside a structure 10 billion light-years across, you would have no way of knowing its edges existed. Every galaxy survey you conducted would show you the interior of the structure, which might look surprisingly uniform, hiding the enormous shape within which you are embedded. This is not necessarily the case. The evidence does not confirm that we sit inside an impossible structure, but the evidence also does not confirm that we do not. And the fact that the question is now scientifically serious, rather than purely philosophical, is itself a sign of how much the landscape has changed. James Webb opened a window that nobody expected to be quite so disorienting. The telescope that was supposed to confirm and refine our model of the universe has instead produced a cascade of findings that each individually demand explanation and collectively suggest that the explanation will require new physics, revised assumptions, or both. The scale of that challenge is genuinely exciting if you appreciate what it means for science. The standard model is not wrong in some amateur, easily dismissed way. It is wrong if it is wrong, in the most interesting way possible, at the very edges of what it was built to describe, in the most extreme structures in the universe, at the earliest times that any instrument has ever probed. That kind of wrongness almost always points towards something genuinely new, and genuinely new, in the history of physics, has always led somewhere extraordinary. Throughout this video, the phrase standard model has appeared repeatedly. Let's be specific about what actually changes if the cosmological principle turns out to be violated at large scales. This is not abstract. The consequences would be concrete, measurable, and would reach into some of the most fundamental things science believes about the universe. First, the age of the universe. The current estimate, 13.8 billion years, is calculated using the expansion rate and the standard model's equations. If the universe is not as uniform as the model assumes, or if dark energy has been evolving over time rather than remaining constant, the age calculation changes, not drastically, but measurably. The universe could be slightly older or slightly younger than current estimates, which would in turn affect how much time was available for early galaxies to form, potentially easing the impossible galaxy tension. Second, the amount of dark matter and dark energy. These quantities are inferred by fitting the standard model to observations. If the model itself is missing something, those inferences could be off. We might have more dark matter than we think, or less. Dark energy might be weaker in some regions and stronger in others. The inventory of the universe's contents, the numbers that appear in every cosmology textbook, would need revision. Third, the interpretation of every cosmological measurement ever made. Distances to galaxies, the cosmic expansion rate, the positions of baryon acoustic oscillations in galaxy surveys. All of these are measured using tools that assume the cosmological principle. If the universe is not as uniform as assumed, those tools have systematic errors baked into them. Every dataset would need to be reanalyzed under new assumptions. Fourth, and most profoundly, the fate of the universe. Whether the universe will expand forever, slow and stop, or eventually reverse, depends on the properties of dark energy and the total density of matter. If either of those changes in a model revision, the predicted fate changes with it. The current consensus that the universe will expand forever at an accelerating rate, cooling and thinning until even the last black holes evaporate, might need to be reconsidered. None of these changes would happen overnight. Science moves through accumulation of evidence, debate, reanalysis, and eventual consensus. A confirmed violation of the cosmological principle would not overturn everything in a single announcement. It would set off years of careful work across every subfield of cosmology, each team revisiting its conclusions in light of the new framework. But the direction is clear. The data is pointing somewhere uncomfortable for the standard model. The impossible galaxies are real. The oversized structures are statistically robust. The Hubble tension has not resolved. The early universe is forming things faster than it should. Something in the foundation is under strain. Physics has been here before. Newtonian mechanics was one of the most successful scientific theories in history, explaining everything from falling apples to planetary orbits with extraordinary precision. Then came Mercury's orbit, which Newtonian gravity could not quite account for. That small discrepancy pointed toward general relativity. The tiny anomaly was the entrance to a completely new understanding of space and time. The anomalies Webb is finding are not tiny. If the standard model needs revision, what might replace it? This is speculative by necessity, since confirmed new physics has not yet arrived. But the shape of the anomalies tells us something about the shape of the solution. The clearest thread running through all of Webb's challenging findings is time. Things in the early universe happened too fast. Galaxies too massive too early. Structures too large too early. Reionization too early. Whatever is missing from the standard model seems to involve the pace of early cosmic evolution. One proposed fix that has gained serious traction among physicists is early dark energy. In the standard model, dark energy appears to have become dominant only in the last few billion years of cosmic history. when the universe had expanded enough that dark energy's constant density exceeded the density of matter. Before that, dark energy was overwhelmed by matter and played little role. But what if dark energy had a brief, intense period of activity in the very young universe? A phase where it contributed significant energy before fading away. This early dark energy would have two effects. It would change the expansion rate of the young universe, altering the scale of baryon acoustic oscillations and shifting the early universe measurement of the Hubble constant upward, closer to the locally measured value. And it would have accelerated the growth of density fluctuations, meaning matter clumped faster, dark matter halos grew bigger sooner, and galaxies could assemble more mass in less time. Both the Hubble tension and the impossible galaxies might be explained by a single ingredient that existed briefly and left its fingerprints everywhere. Early dark energy remains a hypothesis. Finding definitive evidence for it requires measuring the baryon acoustic oscillation scale at multiple cosmic epochs with extreme precision, exactly what Euclid and Roman are designed to do. If early dark energy is real, those surveys will find a specific pattern in how the baryon acoustic oscillation scale changed over time. If it is not real, the pattern will be absent. Another possibility involves a modification to how dark matter behaves. The standard model assumes dark matter particles are cold, meaning they move slowly and cluster easily. But if dark matter particles interact with each other, or with ordinary matter through some force we have not yet detected, they might behave differently on small scales. They might cluster into halos that grow faster under certain conditions, producing the oversized early galaxies Webb is finding. This would also leave specific signatures in the cosmic web's small-scale structure that Euclid and Roman would detect. A third direction involves rethinking inflation, the period of explosive expansion right after the Big Bang that set the initial conditions for everything. Standard inflation models produce a universe that is extremely uniform on large scales. But if inflation was slightly different from the simplest models, it might have seeded density fluctuations on larger scales or with different characteristics, giving rise to structures like the Big Ring and the giant arc that sit outside what standard inflation would allow. The beautiful thing about all of these possibilities is that they are testable. Each one makes specific predictions about the distribution of galaxies, the shape of the cosmic web, the behavior of baryon acoustic oscillations, and the properties of the cosmic microwave background. The data needed to distinguish between them is being collected right now. Science fiction resolves its mysteries in dramatic moments. A single experiment, a brilliant insight, a quiet afternoon in a laboratory when the answer finally clicks. Real science moves differently. It moves in data releases and conference presentations and preprint papers and peer reviews and follow-up observations and corrections and debates that sometimes last decades. The resolution of what James Webb has started is going to take time. But the timeline is clearer than it might seem. Within the next 5 years, Euclid will have mapped several 100 million galaxies across a wide slice of the sky. Roman will add hundreds of millions more, with complementary coverage and wavelength range. Webb will continue its deep, pointed observations, confirming and characterizing individual galaxies and structures at the frontier of cosmic time. The combination of wide, shallow surveys from Euclid and Roman with deep, detailed observations from Webb will give cosmologists the most complete three-dimensional picture of the universe ever assembled. Specific questions will get answers. The Hubble tension will either persist and deepen, eventually forcing a revision to the standard model, or systematic errors will be identified that bring the two measurements into agreement. Early dark energy will either leave its fingerprint in the baryon acoustic oscillation data, or it will not. The Big Ring and the giant arc will either be confirmed as genuine violations of the theoretical size limit by statistical analysis of a much larger sample of the sky, or they will be shown to be rare but plausible fluctuations within an otherwise standard model universe. The Hercules Corona Borealis Great Wall remains the most uncertain of all the structures discussed. It has never been confirmed by independent teams using different methods. The gamma-ray burst clustering signal that reveals it is real, but whether it traces a single coherent structure or a chance alignment of separate concentrations of matter is still genuinely open. New gamma-ray burst data and more sophisticated statistical analysis over the next decade will be decisive. Population: 3 stars. The first stars in the universe may be directly detected by Webb within this decade. Finding one would be one of the greatest discoveries in astronomical history and would constrain models of early star formation with extraordinary precision. The fate of the cosmological principle itself will become clearer as sky surveys grow. If the universe has genuinely lopsided structure or preferred directions, those signatures will become statistically undeniable as the mapped volume of the universe grows. If the universe is truly uniform at large scales, larger surveys will show that the anomalies cluster near the theoretical size limit and do not extend further. In science, the most honest answer to when will we know is sooner than you expect from the outside and later than it feels from the inside. Progress is slow in the making and sudden in the appearing. One day, in the next decade, a dataset will come out that shifts the conversation definitively. Everyone who has been following the field will recognize the moment when it arrives. Until then, the anomalies remain, the tensions remain, and James Webb keeps watching. There is something almost personal about what James Webb is doing. Every image it sends back is a message from the past. Light that left a galaxy 13 billion years ago, before Earth existed, before the sun formed, before the rocky materials of our solar system had even assembled, has traveled across the entire observable universe and arrived at a gold-plated mirror in space that humans built and aimed at exactly the right spot to catch it. That light carries information. The spectrum of a galaxy tells you what elements it contains. The brightness tells you how many stars are burning inside it. The shape tells you whether it is merging with a neighbor or spinning peacefully alone. The distance tells you when, in cosmic history, you are looking. Every pixel in a Webb image is a data point from a specific moment in the life of the universe, delivered to us after a journey billions of years long. What Webb is doing, fundamentally, is reading the universe's autobiography, chapter by chapter, going backward in time, finding out what was there, before what we see now, and before that, all the way to the earliest pages when the first stars lit up in the dark. The autobiography has surprises in it, things that did not match the story we had written in advance, chapters that are longer or shorter than expected, characters, the impossible early galaxies, the oversized structures that do not fit the plot the way we assumed. That is how science works at its best. You build the best model you can with the evidence available. You make precise predictions. You build a machine to test those predictions. And when the machine finds something your model did not anticipate, you have to confront it honestly. You cannot ignore it. You cannot explain it away if the evidence is strong enough. You have to go back to your model and figure out what it is missing. James Webb is forcing exactly that confrontation. The impossible galaxies are not going away. The oversized structures are not statistical noise. The Hubble tension is not a measurement error waiting to be corrected. These are real features of the universe that our best model cannot fully account for. They are the places where the autobiography departs from the story we wrote. And here is the thing about those departures. Every time in the history of science that an observation could not be explained by the reigning theory, what came next was bigger than what came before. Maxwell's equations explained the speed of light and directly led to special relativity. Special relativity and the perihelion of Mercury directly led to general relativity. The ultraviolet catastrophe in blackbody radiation directly led to quantum mechanics. The anomalous expansion of the universe directly led to the discovery of dark energy. Each time the universe refused to fit the model that replaced it was more complete, more powerful, and more strange than the one it superseded. The universe has a pattern of being weirder than we think, and then weirder than that. Webb is showing us where the current model runs out. That is not a failure of science. It is science doing exactly what it is supposed to do. Step back from all the specific findings and look at the full picture. In just a few years of operation, James Webb has found galaxies that assembled faster than physics allows, mapped the cosmic web back to within 1 billion years of the Big Bang, helped confirm structures larger than the theoretical maximum, sharpened the Hubble tension, and given us the first serious candidates for the ancient universe's first generations of stars. The list is extraordinary for a single instrument in such a short time. But the thing that should genuinely give pause is not any individual finding. It is the possibility that all of these findings are connected, that the impossible early galaxies, the oversized cosmic structures, the Hubble tension, and the hints of large-scale anisotropy are not separate, unrelated anomalies, but symptoms of a single underlying gap in our understanding. A gap that the standard model cannot bridge because it is missing an ingredient, a force, a behavior, or a property of space itself that controls how matter organizes on the very largest scales. If that gap is real, it means that the 4% of the universe, made of ordinary matter, the stuff you can see and touch, is embedded in a larger structure of dark matter and dark energy that behaves in ways our best model does not fully capture. The 96% of the universe we cannot directly detect is doing something our equations do not quite describe. The scale of what we do not know is enormous. Dark matter has been confirmed to exist by its gravitational effects on galaxies for nearly a century, but not a single dark matter particle has ever been detected directly. Dark energy fills 68% of the universe's energy content, but has never been measured as anything other than its effect on cosmic expansion. Cosmic strings are predicted by theory and have never been seen. The cosmological principle is assumed by every major cosmological model and has never been rigorously proven to hold. Science is comfortable with not knowing. Uncertainty is not failure, it is the engine. Everything that is not yet understood is a question that eventually gets answered, and every answer produces better questions. The history of physics is a history of comfortable certainties being replaced by more accurate and more surprising truths. What James Webb has done is take several things that were quietly uncertain and make them loudly uncertain. It has raised the volume on questions that were already present at a murmur. That is valuable. That is exactly what a $10 billion telescope should do. Not confirm what we already believed, but show us where what we believe falls short. The universe is approximately 13.8 billion years old. It contains approximately 2 trillion galaxies. It spans approximately 93 billion light years, and across that entire incomprehensible expanse, at scales from individual stars to structures 10 billion light years long, something is organizing matter in ways that our best current understanding cannot fully explain. That gap is the most exciting thing in science right now. Every discovery in this video is billions of light years away, billions of years in the past, operating on scales that have no connection to daily human experience. The Big Ring is 9 billion light years from Earth. The Hercules Corona Borealis Great Wall is 10 billion light years long. The impossible galaxies existed when the universe was less than 500 million years old, long before Earth, long before the Sun, long before the raw materials of our solar system had even been forged in the deaths of earlier stars. So why does any of it matter? Because understanding how the universe works is not separate from understanding what we are. Every atom in your body was forged in a stellar core. The carbon in your cells came from a star that lived and died before the sun was born. The iron in your blood was created in a supernova explosion billions of years before Earth formed. You are made of the universe. What the universe has been doing across 13.8 billion years of history is the backstory of your existence. Finding out that backstory is not complete, that something important is missing from our picture of how the cosmos assembled itself, is directly relevant to the question of how we got here. The cosmic web that James Webb is mapping is not just structure for its own sake. It is the architecture that led to star formation. Stars led to heavy elements. Heavy elements led to rocky planets. Rocky planets led to chemistry. Chemistry, under the right conditions, led to biology. Biology led to minds that can point telescopes at the universe and ask questions about it. Every node in that chain of causation traces back to the cosmic web and the dark matter that built it. If the standard model is missing something, if dark matter behaves differently than we think, or if dark energy has been evolving, or if the early universe had ingredients we have not yet identified, those missing pieces were present at every step of that causal chain. They shaped the web that built the galaxies, that produced the stars, that forged the elements that became you. Knowing them more completely means knowing your own origin more completely. There is also a practical, deeply human reason to care about the Hubble tension specifically. The age of the universe is calculated from the expansion rate. If that rate is higher than the early universe measurement suggests, the universe might be slightly younger than 13.8 billion years. Or if something more exotic is going on, the calculation might need to be revised in ways that shift our sense of cosmic time significantly. The age of the universe anchors everything in astronomy. It sets the clock against which all other cosmic events are measured. And finally, there is the simple fact that we are probably living at a special moment in scientific history. The last time cosmology faced a crisis of this magnitude, it was in the 1990s, when the discovery of cosmic acceleration forced the introduction of dark energy and rewrote the standard model entirely. That crisis was resolved by better data, new theoretical ideas, and eventually a Nobel Prize. The current crisis, driven by Webb and sharpened by the surveys beginning now, has the same character. Something real is challenging, something fundamental. The resolution, when it comes, will almost certainly produce a picture of the universe that is stranger, larger, and more extraordinary than the one we have now. That is the promise sitting inside every impossible galaxy and every oversized structure that Webb has found. The universe is bigger than our model of it, and we are finally building tools good enough to find out by how much.